The continuation.
Elias Usoswe.
So we have, we go to C now. So C again, if you look at C, so we're approaching, as you go to 5. Now, this function, as I said, you wanted to ask as x goes to -5. Because if it's to 5, we have nothing much to do but to just substitute. We just substitute, we'll have 3 by 5 divided by 2 by 5 plus 10. That will be 15 divided by 20, which is equal to 3/4. So for as long as when I substitute, it makes sense, that's okay. Then we have this one here. As x approaches 0, even if I don't substitute, even if I don't sketch this function, I can still approximate the limit here. Because then what we'll do is, we'll have the limit as x approaches 0 of -1 over x squared x plus 1. So here, we can substitute 0 there. So we need to study this in 2 ways. The limit as x approaches to 0 from left of this. So that means you are moving to 0 using negative numbers. Now, if you put a negative number here, it becomes positive. So our interest is here. Okay. So you can't go that far to -1 because -1 will make the whole thing undefined again. So you're moving in the space between -1 and 0. Now, all the numbers between -1 and 0 are actually less than 1. So when you have a negative number less than 1, I mean, that is bigger than -1 but less than 0, added to 1, it will give you a positive value. Meaning that because the top part is negative, all the values you'll be getting there will be very small. There will be negative values. Okay. So an example I would give is -1/2. So we have -1 over -1/2 squared, -1/2 plus 1. This will be -1 over 1/4 +1/2. That's -1 over 1/8, which is -8. So the values of that we get are negative values. So they will keep going down. If I picked a -1 over 1/3, the value there would have been bigger than, should have been bigger in numerical value, but with a negative sign, meaning very small. So this means that the limit here actually goes to -infinity. So the thing that you should notice here is that we'll be talking about these in terms of asymptotes. Okay, so even if you were to move from the right, the same thing would happen. So the values will be, as they become small, they'll be going to the negative because on the right, they'll all be positive, and there's a negative number up there. So that will be putting them down. So we'll still be getting a negative, so that the whole limit as x approaches 0 then is going to be -infinity. Because even if you compute from right, you still get the same thing. Okay. If you talk about E, the limit of x goes to 7. Again, it will be the same thing, except that now, because of the square, the numbers will be positive. So it will blow up to positive infinite. And so here it will be positive infinite because the numbers are so. The idea here is you want to check how the values are changing. Are they changing to negatives or changing to positives? Are they changing at a faster rate, or maybe it's not that fast? So those movements will guide you on whether you reach infinite or you reach minus infinite. Okay. And then the tan, again, it's not so difficult to see, even if I don't know how to sketch tan. You think of numbers, so you're moving to 90 from left. So you would substitute, for example, what happens if I substitute tan 0? Okay, 0, I'll get 0. Okay, what about tan 30? Okay. Okay, after tan 30, what about tan 45? What about tan 60, for example? So these will tell you whether the numbers are increasing or not. But once you know that tan 90 is undefined, then you have a gist that, okay, so if it's not defined and my numbers are increasing, then the whole thing will go to positive infinity. Because then it's hitting into the asymptote, so it will blow up. So it will blow up like that. So it's not that much complicated if you think about it in substituting. So I'm now trying to dodge sketches and trying to get another way of doing things. So here they're saying you're going to 0 from left here. So again, that's cosec. So you check the limitations of cosec. Okay, cosec is 1 over sine. If you want to get anything right, you write as 1 over sine, and then work out your mathematics, and then substitute the angles as you get closer to 0. Because remember, sine 0 has an asymptote there. It's not defined. Okay, so I want to leave those other two for you guys to check in the same context, so that we can do the ones on limit on infinite now. As the limit approaches infinite, so the easiest approach here, I think we did talk about this the first time I taught you calculus, you guys. I told you that you can just factor out the highest degree in the denominator and the numerator, and then evaluate the limit using the factor. The limit as s goes to infinity of 1 over x is 0. So that's what we're going to use here, there, and here. So I don't need to repeat this unless otherwise, but you can see when you just look at them, you know the limit. The first one, the limit is 0. The second is 3 over 2. The third, it's 0. And those you know what I'm talking about now, because we did them. Unless otherwise. Okay. So we advance a bit. We are now looking at continuity and the definition of the derivative. So again, we define the term continuous, what it means for a function to be continuous. And I'll remind you here. So this is what we talked about. We say that f is going to be continuous at x is equal to c if the first thing, f of c, is defined. The second thing, the lim as x approaches c of f exists. And third, the same lim as x goes to c of f is actually f of c. So when that happens, then you say the function is continuous. Remembering that the limit will exist if and only if the two side limits are equal. So that's the most key thing there. So now we go to part A. Is the function f continuous at x is equal to -1? So first thing we need to do is 1, what is f of -1? F of -1 will be -1 squared minus 1, which is 1 minus 1, giving us 0. The second thing would be the limit as x approaches -1. So now, if you look at -1, there's only one function that has -1. Okay, so as x approaches -1, there's only this function here. Have you seen the interval? The interval is -1 to 0. So the fact that the function is defined at x is equal to -1, it means that the limit will utilize the same function. And so we'll have -1 squared minus 1, which is equal to 0. And because the two are equal, which is the third property, we say that f is continuous at x is equal to -1. So you just want to check if it's defined, if the limit exists. And if the limit exists and is defined, then you check if the values are equal. Okay? The next thing will be, is f continuous at x is equal to 1? Is it continuous at x is equal to 1? Hello?
Yeah. I'm asking if you can repeat the last statement you said about the limit, if it's continuous or discontinuous.
So we are saying, the limit is never continuous. It's a function f which is continuous or not. And the function becomes continuous if the limit exists and the same limit which exists gives you the same value as f of that number. So here we're looking at x approaching -1. So we want the limit as x approaches -1 to be equal to f of -1. When that is the case, then we'll say the function is continuous there. So let's go to this one.
So the way the first question was saying is f continuous at x is equals to -1. Then since we found f of negative is 1, so that means that f is not continuous. Eh?
What is f of -1?
F of -1 is 0.
What is the limit as x approaches -1?
Yeah. It's 0.
So they are equal. So it's defined, it exists, and the values are equal. So it's continuous. So when it's defined, it gives you a value. When the limit exists, it exists as a value. Then you compare the two values. If the two values are equal, then f is continuous there.
Okay, thank you.
So now let's go to part 2. At x is equal to 1. So first thing, what is f of 1? Now, when x is 1, the function is given as 1. So f of 1 is 1. 2, the limit as x approaches 1. Now, there are two directions here. You can approach 1 from the left or 1 from the right. So we check from the left first. From the left, remember we said from the left you use less. So we pick x less than 1. So that would be 2x, giving us 2. Then also the limit as x approaches 1 from right. So 1 from right, you pick minus 2x plus 4. So you get minus 2 plus 4, which is equal to 2. So you see, from left and from right, we're getting the same number. So this means that the limit as x approaches 1 of f is equal to 2. So it exists and it is 2. The question is the limit equal to f of 1? Now f of 1, so now we're on part 3. Part 3 compares the two. So we have the limit as x approaches 1 of f coming out to be 2, which is not equal to f of 1, which is equal to 1. This means that f is not continuous.
So how do we know, like, we have to use a certain equation for maybe if x is approaching 1 from the left and x is approaching 1 from the right? How do we know that we're supposed to use this equation or that equation?
When x approaches any number from left, you use the equation which is coming from x less than that number. When x is approaching n number from the right, you use the equation which says x is greater than that number. So that's how you know.
All right.
Sir, sorry, sir. What of on A? How did you find which equation that you use for x is equal to -1?
So x is equal to -1 only appeared once. And the time it appeared, the -1 was included. So we didn't bother to look at any other direction because we are only seeing -1 once. So we could pick the limit because the function is defined at that value. We could also pick the value because it's defined also at that value. Then we could also pick the limit because it exists at that value. So had we seen one appearing twice, I mean -1 appearing twice, we would have picked two functions. Okay. At what values of x is f continuous? At what values of x is f continuous? So from what you have seen, f is not continuous at x is equal to 1. And so we must check if f is continuous at Maybe we should first answer which one now. Okay, so let's check also at 2. So maybe if we check at 2, at 2, we have issues because who can tell me the limitation that 2 is having there?
Isn't it that the function is 0?
At 2. Who is able to see which function includes 2?
Okay, the last one.
So you can't tell which function includes 2. It means that f of 2 is undefined. Because we can't say what f of 2 is. There's nowhere where it's included. So it means that for the limit we can find the limit as x approaches 2 from left, we'll go to x less than 2 and substitute there in this guy. That would be 0. Also the limit as x approaches 2 from right, we'll substitute 0, so we get 0. So you see the limit exists and it is 0. But the challenge is f of 2 is not defined. So then there's this question. What value should be assigned to f of 2 to make the extended function continuous at x is equal to 2? So if they ask you to determine what the value of f of 2 should be, your answer is it should always be the value of the limit. So we want f of 2 to be equal to 0 so that it will then be equal to the limit as x approaches 2 of f of x. Then it will be continuous. Because remember the condition says f should be defined there and the value should be the same value as the one for the function. Okay, so at what values of x is f continuous? So f is continuous from -1 to 1. It's also continuous from It's also continuous from 1 to 2, in between there, and also from 2 to 3 in those open intervals, and not on other boundaries, since we have checked. So this I'm using the principle of the graph. Remember I said if you are graphing and there's no lifting of a pen, for better better terms. For lack of better terms, then we could say that the function is continuous through there. Then they're saying, to what new value should f1 be changed to remove the discontinuity? Remember what we got at 1. At 1, we said the limit as x approaches 1 of f of x, it was coming out to be 2. And yet f of 1 was giving us 1. This question is asking us to say, for what value of f what new value should f1 be changed to in order to remove that discontinuity? So you say, okay, to change, I will change f of 1 to positive 2. Like that. Because you know that it's not easy. In fact, it's not even possible to change the limit to meet the value of f. It's only possible to change the value of f to meet the limit. That's how you answer such questions. So here you seem like you guys are being forced to think. And you just have to think anyway. That's why you chose school. Question 2. Define F3 in a way that extends F to be continuous at x is equal to 3. So already that gives you a hint that it's not continuous. So we have, hello.
Sorry, take you back. On the last one, where you said that what value should be assigned to f of 2 to make the no, like to what new value should f of 1 be changed to remove the discontinuity? I didn't get what you said. Is it the same one for? Is it the same one that we was this that we made it to be the limit to be equal to f of what? F of I don't know, the one that gave us 0.
These two questions are different. This was f of 2. There was f of 2, then there's f of 1. F of 2 was giving us 0. F of 1 was giving us 1. And we answered the continuity of f of 1 here. Remember we said at x is equal to 1, f is not continuous, is it? That meant that f is discontinuous there. So if f was discontinuous there, we are saying, why was it discontinuous? Because the limit value and f of 1 were different. So to make them the same, what should f of 1 be? That's what this question is asking. So it should be the value of the limit. Okay. So let's go to 2a. 2a, the first thing you do is you get the limit as x approaches 3. X squared minus 9 over x minus 3. That will be the limit as x approaches 3. X minus 3, x plus 3 over x minus 3. So we have this and that. So we get the limit as x approaches 3 of x plus 3 to be equal to 3 plus 3, which is equal to 6. Immediately you find the limit. Then you've answered this question. Define f of 3 in a way that extends this so that it is continuous. So you just say f of 3 should be equal to 6. Because initially f of 3 was undefined. If you substitute direct, you'll get undefined. And now we have the limit. The limit is 6. So we want it defined so that we have the limit existing. But not just defined, but defined as 6. Okay? Define g of 2 in a way that extends g to be continuous at x is equal to 2. So again, you factorize the numerator there. When you factorize it, it will come with x minus 2 up. Then you cancel with the down part. Do the evaluation. The value you find is what should be a g of 2. The value you find for c as the limit value is what should be h of 1. The limit value you find for f in D is what should be your f of 4. The same is extended to part 3a. For what value of a is f continuous at every x? So you find the limit from left. The limit must be the same as from right. Then that limit should be the same f of 3. So you substitute the f of 3 there, you get 6a. So 6a should be equal to the limit you get in part 1.
Sir, what? Like, what are you saying? The limit we get in what?
Sir, stop some question 3A. Then you leave B.
So you do, you can actually find the value of a by getting the limit as x approaches 3 from left. You use this one. Remember x less, so you have 3 squared minus 1, which is equal to 8. The limit as x approaches 3 from right, it will be 2ax. When you substitute 3 where there's x, you get 6a. Now, if this function is to be continuous, the first thing is that these two limits should be equal. So 6a should be equal to 8. That's the only way we'll have a limit here. So meaning that a is equal to 8 over 6, which is equal to 4 over 3. Point number 1. So we have found the value of a, for which the function will be continuous. And the function here will be continuous no matter what happens. This is the a you wanted. That's how you're going to find b. You find, so you have -2 there. So you want for 4b to be equal to -2. And so you find b. You see? Not equal. You see? Not equal. Majodara.
Excuse me. Hey.
Ah, sure.
Majodara, my chips.
Excuse me, sir.
Yeah.
What? Ah. Anyway, it's right. It's right.
Yeah, it's good that it's all right, man. Things just have to be right.
Okay.
Otherwise, guys, the basic principle of life is that you need to enjoy what you chose, eh? So enjoy your choice. Including math. You chose math, right? Enjoy it. Okay, so maybe let's not do derivatives today. Let me just leave you thinking about the limits thing. So fix up the gaps.
Sir.
We continue with the
Let's
limits.
do so that we revise. Yeah, so that we can revise now after we do.
No problem. So let's give it 10 minutes more. Give it time to load,
Sir, meaning
then we come back.